Hi, my name is Madeline,
I'm Jada.
I'm Xavier.
and we are Team 1064 from the University of Florida, and this is our model for problem A. In our presentation, we'll cover the context of the problem, including some background research, discuss the three data sets we used in our model, describe our modeling framework, report our findings, and discuss some of the limitations of our model. First, we're going to talk about heavy metal absorption in the human body. For this problem, we decided to focus on lead and cadmium since there are two heavy metals whose toxicities raise greatest concern amongst medical professionals. About 40 to 50% of orally ingested lead is absorbed into the bloodstream, whereas only about 6% of cadmium is. But it's important to note that cadmium is known to have a very, very slow excretion rate. As for the biological processes that take place, lead is distributed to the brain, liver, kidney, and bones, while cadmium is typically stored in the kidneys and liver. Long-term exposure to and bioaccumulation of lead in the body can lead to lead poisoning, which can cause damage to the central nervous system, mental and behavioral problems, and decreased intelligence scores. Such exposure and bioaccumulation of cadmium can cause kidney and bone damage, along with increased risk of lung, kidney, prostate, and pancreatic cancers. Effects of metal toxicities are not limited to this list, but they are the bodily damages that occur most frequently. For chocolate data, we pulled data for the 7 countries listed here. The report presents daily chocolate consumption per capita on average in 2022. The data is given in grams per capita per day. For concentration per country per day, we gathered the average lead and cadmium concentrations in chocolate distributed in each of the 6 countries of interest. It's important to note that while these metals pose detrimental effects in high concentrations, acute exposure can accumulate in the body over time.
For our last data set, we considered age data, and we created a randomized sample set of hypothetical subjects with 30 children from ages 1 to 18 from each of the different countries. Each subject is given a randomized age and a randomized weight, and the CDC provides weight for age data from which we took the acceptable range of weights for each age and randomly assigned a weight to each child. We also included life expectancy in days for each child, which was taken from the CIA database on country comparisons.
The first assumption we made was that the daily consumption per capita data we found online is true. We also displayed these metrics in the table on the left-hand slide below. Next, we assumed that our hypothetical subjects lived to the life expectancy of their given country. Additionally, we assumed that each brand of chocolate in a given country had the same concentration of heavy metals and that all chocolate eaten is contaminated. Finally, we took into account that each of the countries celebrated different holidays. We assigned a certain amount of time and days to each respective holiday to include in our model.
So this is our basic modeling framework. The change in concentration of metals in your body over time is equal to Km times I of T minus R times E of T, where I of T is the ingestion and E of T is the excretion rate. And M is the concentration of metals, and K and R are the absorption and excretion constants. So every year we consume a certain number of grams of chocolate. For each gram of chocolate, there's a concentration of micrograms per gram of chocolate. And for every microgram of this lead ingested, around 50% of it is accumulated in the bloodstream. The half-life of lead in the bloodstream is about 30 days. So we incorporated an exponential decay function into our model. Our concentration of lead is relative to our intake, I of T. And the term negative K times C of T indicates that the higher concentration of lead in the bloodstream, the faster the rate of the lead concentration is lowering. This is due to the natural response factors in our bodily processes. We assume that chocolate consumption patterns over the course of the year follows a mixed normal distribution. There are spikes at major holidays, like in the US, for example, Valentine's Day, Halloween, Christmas, as well as birthdays. And we can adjust for the magnitude of each spike with each density's function's respective variance. The sum of the weighted densities represents the combined frequencies at each of the n consumption spikes. Multiplied by the lead and absorption factors gives us the function of lead accumulation in the bloodstream through the consumption per day, the integral of which gives us the total accumulation over the course of the year. Because each individual density function has an associated area of 1, we multiply each function by a weight W sub I to scale and adjust the net consumption across the year. Here is the final model written out. The following graphs show the distribution of lead accumulation through consumption in red and the expected lead concentration levels throughout the year in blue. We assume that this person in these examples consumes a fixed 22 micrograms of lead a year and accumulates approximately 11 micrograms per deciliter a year. purely from intake. The average concentration of lead in the bloodstream is approximately 1.4 micrograms per deciliter, and the real unsafe levels occur at about 3.5 micrograms per deciliter. We kept the main spikes of consumption constant, like the major U.S. holidays like Valentine's Day, Christmas, and Halloween. So this first graph assumes a birthday in the beginning of the year. This is a birthday in the middle around summer, the respective concentration. And this is assuming a birthday late in the year around Christmas and Halloween. And this final graph assumes like uniform assumption across the year. And the average consumption of lead is through chocolate is 0.06 micrograms a day. So 0.03 micrograms per deciliter absorbed a day. And this final graph shows how a more uniform consumption of chocolate through the year maintains the healthiest and lowest levels of concentration in the lead in the bloodstream throughout the year.
In our model, we consider the potential lifetime average daily dose, or LADD, which accounts for how the metals will affect children while they are still developing more than if they were fully grown adults. The LADD is calculated over time using the same equation that accounts for the increased exposure to toxicity from eating contaminated chocolate as an adolescent. The two measures of the severity of exposure to metals that we are concerned with are hazard quotient and hazard index. The hazard quotient is calculated by dividing the average daily dose by the reference dose, or the estimate of daily oral exposure to heavy metals. We calculated the hazard quotients for both lead and cadmium for each subject. The hazard index is simply the sum of the hazard quotients for all heavy metals considered. If either of the hazard quotients or hazard indices are greater than or equal to 1, this suggests that the intake of heavy metals is at a dangerous level and warrants an immediate change in diet or lifestyle. We created a series of histograms in R, and the one on the left shows the hazard indices for each child when we assume the same amount of chocolate is eaten every single day, whereas the graph on the right shows the range of hazard indices when we include the observation of certain holidays. There is a clear increase in the values of the indices when more chocolate is consumed over the holidays for each respective country, which is to be expected. For India, this trend is observed as well, where the holiday chocolate consumption spikes. When there is no change in the amount of chocolate eaten per day, the majority of people have a relatively safe level of heavy metal consumption, with a few between 1 and 2. The inclusion of the holidays, the range jumps to a maximum level of 3. However, children in Turkey are faring far worse, as their hazard index values are incredibly high, even without the spike for the holidays. With the inclusion of holiday consumption, the values increase to dangerous levels of acute exposure. In Germany, the values are in a healthier range, and we see the same trend as previous countries. For Italy, there are also no hazard index variables below 1 for either of the models. Thus, there is not much of an increase in index values when more chocolate is eaten over times of celebration. For Malaysia, the data is ideal, as the histogram shows how all of the children had hazard indices less than 1 when not accounting for holidays. Malaysia has the most amount of days spent eating more chocolate since they celebrate 3 major holidays, but the hazard index values are still incredibly low compared to all other countries considered.
Now we're ready to present our results. Having a birthday near a holiday yields a more dangerous bioaccumulation of heavy metals in the body as opposed to having a standalone birthday in the middle of the year. Further, uniform consumption of chocolate throughout the year is healthiest for a child. The long-term patterns for an individual illustrate an increase in heavy metal bioaccumulation, leading to negative health effects. While these habits for a year or two may not be detrimental, a lifetime of eating contaminated chocolate can have severe consequences. Our data ranges from low daily chocolate consumption to high consumption in various countries, but the results are largely the same for each country, which is when there's a spike in consumption for holidays, the hazard index goes up. Binging during the holidays rather than enjoying chocolates throughout the entire year leads to a higher susceptibility of health issues. Thus, parents should encourage their children to enjoy their chocolate slowly over time. The results for the hazard indices are displayed in the table. All of the countries that had children in the safe zone to begin with ended up with fewer children with safe levels of heavy metals in their bodies once holidays are accounted for. Our first limitation is a lack of data specifically on children. Our chocolate data set includes data based on an entire country's population, not just children. We also made some assumptions for simplicity. Our hypothetical subjects are assigned constant lifespan and chocolate consumption in their respective countries. We did not account for variability in these two values within a country. Finally, some of the questions asked in the problem were ambiguous, so we addressed them based on our best interpretation. For example, we found the phrase user model to determine long-term patterns for an individual unclear whether it was referring to accumulation, consumption, or another factor. And that concludes our presentation. Thank you all for your time and consideration.